If you have ever taken a class in discrete maths or combinatorics, you might have come across the following exercise where we are asked to calculate the number of ways a 2x(n) board can be tiled with 2x1 domino tiles. If this is the first time you ever heard of this question, it may seem fairly hard. There neither seems to be an obvious way to order the tilings, nor to make sure that you have accounted for all the possibilities. So, how do we go about this? Let's first give the thing we are looking for a name, since names make most things less scary. So from now on, we will write Fn for the number of ways to tile the 2x(n) board. Also, it is always a good idea to compute the first few values to hopefully get some inspiration. For F1, we really have only one possibility, and for F2, we have two ways. Either we place both tiles horizontally or both vertically. For F3, the problem already becomes a bit trickier, but we can still figure out that we have the following three tilings. With even more work, we get for F4 5 different tilings. At this point, we might notice that, at least for the first few terms, that the number of tilings is always the sum of its two predecessors. Let's look a bit more closely at the tilings themselves now. Comparing the tilings of the 2x1, 2x2 and 2x3 cases, every tiling for the 2x3 case can either be constructed by attaching two horizontal tiles to a tiling of a 2x1 board, or one vertical tile to a tiling of a 2x2 board. The same holds true for the 2x4 case. In general, given a 2x(n) board, a tiling can either have its rightmost two squares filled with one vertical tile or two horizontal tiles. So, by definition, there are Fn-1 and Fn-2 ways respectively to tile the remaining board, showing that Fn equals Fn-1 plus Fn-2. You might have seen this formula before, since this together with the starting value 1 really is just the recursive definition of the Fibonacci numbers, or rather the n+1th Fibonacci number depending on your definition. Either by knowing Binet's formula, which gives an explicit way to calculate Fibonacci numbers, or by using the recursion in some time, we can now calculate that there are this many ways to tile a 2x42 board. The natural question now is, of course, what the answer for general m×n boards is. That is, when we don't restrict the size to only 2 in the first dimension. Unfortunately, the derivation for that is far more complicated than what we just witnessed, and to my knowledge can't be solved with one simple recursion. But on our journey to get a final satisfactory answer, we will make use of a wide range of tools involving both graph theory and a surprisingly big amount of linear algebra. For the sake of familiarity, let's consider for now a typical 8x8 chessboard. It is always a good idea to rephrase the problem to something we are more familiar with. So let's discuss what we actually mean by a domino tiling. As suggested by the colors, a domino always covers two neighboring squares, one of which is black and the other white. Also, when we talk about tilings, we of course do not want the tiles to overlap, meaning that every black square is to be matched to a unique neighboring white square and vice versa. As our first step, instead of thinking about the board itself, we can think about a graph where each square is represented by a vertex and two squares being adjacent is indicated by an edge. This gives us this bipartite sort of grid-like graph that is in some sense dual to the grid-like graph separating the squares of our original board. In this new setting, a tiling is represented by a subset of the edges where every vertex is endpoint of exactly one of its edges. This corresponds to the fact that each square of the original board is matched with exactly one of its neighboring squares. Therefore, such subsets of the edges are known as perfect matchings. So, as a first reduction, instead of counting the number of tilings of an m×n board, we count the number of perfect matchings in this m×n grid graph, which we will from now on call GMN. Now, let's utilize the fact that the graph is bipartite. For that, let us look again at the graph G88 and enumerate its black and white vertices from 1 to 32 respectively. As we have observed, a match can only happen between vertices of opposite colors, and for a perfect matching, each vertex has to be matched. We can therefore think of a perfect matching as a sort of mapping from each black vertex to a white vertex. Because for each vertex the match is unique, this mapping has to be bijective, and using the labelings of our vertices, we can think of it as a permutation of the numbers 1 to 32, or in general 1 to m times n halves. We don't want to drag this expression around, so we'll define m times n halves to be capital N. From this, we have now gathered some more insight into our problem. For example, if m and n are both odd, the m times n vertices of the corresponding grid graph can't be divided up into two equal-sized groups of black and white. So in this case, it is in fact impossible to find a perfect matching. Also, with the labeling fixed, every perfect matching corresponds to a unique permutation, so the number of perfect matchings is at most capital N factorial, which is not a great upper bound, but maybe a start. There are clearly permutations which do not correspond to a perfect matching, since we haven't yet accounted for the fact that the black and white vertices in a match have to be neighbors, so we should be able to improve that upper bound and will in fact even arrive at an exact result. To do this, we will need a couple more definitions. We define Bij to be 1 if the ith black vertex is adjacent to the jth white vertex, and otherwise 0. Then, for our permutation sigma, we can just take the product over all Bi sigma I. If the permutation corresponds to a perfect matching in our graph, the product will be equal to 1. If there are two non-adjacent vertices being matched by sigma, one of the Bi sigma I will be 0, making the whole product 0 as well. So, if we take the sum over all possible permutations of this product, we get the following for the number of perfect matchings. Here, Sn denotes the set of permutations of the numbers 1 to n. Let's take a second to look at this formula we just derived. Does it look familiar to you? This is in fact, apart from the sign of sigma missing, just the Leibniz formula for the determinant of the n by n matrix B with entries Bij. This matrix is known as the biadjacency matrix, as it encodes all the adjacencies in a bipartite graph, and as we saw, the determinant of this is nearly the thing that we want. The expression without the sign is called the permanent, and while looking deceptively similar to the determinant, it has no real geometric meaning and is very hard to compute as it doesn't behave nicely under row operations. But maybe we can still make it work. What if instead of the Bij being either 0 or 1, we choose some different values to cancel out the sign of the sigma term? If we could do this, we would only have to take the determinant of that new weighted matrix and proceed from there. As a reminder, the sign of a permutation is either 1 or -1, depending on the parity of the permutation. One way to think about the parity is to count the number of inversions and see if it's even or odd. What inversion means in this context is that for I less than j, I gets mapped to something larger than j. So it just means a reordering of two numbers relative to each other. Concretely, if we were to draw the permutation by connecting each number to its image, the number of inversions corresponds to the number of crossings. If it's even, the sign is 1, and otherwise -1. In particular, if we were to apply the permutation that swaps exactly two elements, so to speak, the sign changes. These special swaps are called transpositions and will be helpful later. Let's proceed to find the necessary adjustments to our matrix. Again, we should first think about a simple example, like the 2x2 board. As we have seen, there are exactly two ways to tile this board, and the corresponding matrix B just has 1 in all of its entries. Using the formula, we see that the terms corresponding to the permutations will cancel due to their signs being different. Of course, we know that the correct answer is 2, so something is still not quite working. We don't really want to change the fact that we are summing over all permutations, and we would also like to keep the sign function, because we are still trying to reduce the permanent down to a determinant. So, the only degree of freedom left are the edge weights. For the 2x2 case, we have one term with positive and one with negative permutation sign. Now, can we maybe change the edge weights on that second matching such that the sign cancels out, while still keeping the product 1? Well, there are many ways to do this, but because we will combine these 2x2 blocks into bigger segments later, we really want the weights on the left and right to be the same. This leaves us with two options, I and minus I. Both would work, but for simplicity's sake, let's just go with I. In general, we will then set Bij to be 1 if the corresponding black and white vertices are connected by a horizontal edge, I if they are connected by a vertical edge, and 0 if they aren't adjacent at all. At this point, it is not obvious at all why this should work in general, but what we are hoping for is that the sign of the permutation and of the product of the weights will cancel out. Of course, the exact value of the determinant will always depend on the enumeration of the black and white vertices. If we had enumerated differently for the 2x2 case, the result would have been -2 instead, and for bigger cases we might even get something imaginary. But all of this will be easily fixed by just taking the absolute value, as long as all the non-zero summons have the same sign. So now, let's show that this is in fact the case. Let M and M prime be arbitrary perfect matchings, and sigma prime the corresponding permutations. If we lay both matchings on top of each other, we get two distinct types of structures. Some matches are doubled, as they were chosen in both matchings. Others form disjoint cycles with edges alternating between a match in M and M prime. This is simply due to the fact that if a vertex didn't get matched the same way in both matchings, the two corresponding vertices also got matched differently, and we can keep going until the cycle closes. Note by the cycles of the edges alternating, each cycle must be of even length. To see the factor by which the signs of sigma and sigma prime differ, we can count the number of transpositions t to get from sigma to sigma prime. As each transposition switches the sign, we get that they differ exactly by -1 to the t. Let's deal with each cycle one by one. If we have a cycle of length 4, or a 4 cycle to be short, we just apply the transposition to the two white vertices to get from sigma to sigma prime. In general, if we swap two white vertices consecutive in the cycle, then the matchings coincide in one more match and the length of the cycle is reduced by 2. Therefore, we can always remove one 2L cycle in L-1 steps. In total, if there are k cycles C1 to Ck, then Chi can be chosen as the sum of the Li-1s. Now, it would be really convenient if for each cycle the factor by which the product of edge weights of M and M prime differ exactly cancels out the -1 to the Li-1. Indeed, we will show more generally that in a 2L cycle of such a grid graph with R interior points and edges alternatingly colored red and blue, the product of edge weights of the blue and red edges differ by a factor of -1 to the R plus L-1. Notice that in our case, R will always be even, since the boundary as well as the entire grid graph both also have an even number of vertices. Now, to show this lemma, it is helpful to think about the region surrounded by our cycle. This part is made out of squares, where two adjacent squares must share at least one side or edge. So you can construct it by starting out with one square and then adding adjacent squares from the outside. To see how the red and blue products change, we slightly shift our perspective. Instead of first building the region using the squares and then alternatingly coloring the boundary cycle, we can first alternatingly color the boundaries of each square and attach them such that the shared sides have opposite color. Then, at the points where we transition to the newly attached square, this scheme will leave the new boundary colored in an alternating way as well. Now we use a little trick. We know that for a square, the red and blue product of weights differ by -1. So if the region consists of A squares, the product over all blue weights and over all red weights, including the inner edges, differ by -1 to the A. But each of the inner edges was counted twice, so the product over the blue weights and red weights of the boundary cycle differ by -1 to the A as well, since the inner edges cancel out. To see that R plus L-1 is the same as A, we first note that if we just look at the single square, the equality is definitely true. Now, we just think about all the ways to add a square. This increases a by 1, so we would expect r plus l minus 1 to increase by 1 as well. If the new square shares one side with the region, then the boundary gets bigger by 2, so l increases by 1, as does a. If the new square shares two sides with the region, the boundary length stays the same, but we get one more vertex in the interior, so r increases by 1. Lastly, if the new square shares three sides with the region, then the boundary gets smaller by 2, decreasing l by 1, but two more vertices are part of the interior, increasing r by 2. This, for the geometers among you, is just a simplified version of Pick's theorem. Think about what we just did. We reduced the question of counting the number of domino tilings to a question about calculating the determinant of a weighted by adjacency matrix by showing that all of the non-zero terms have the same sign, which means that the determinant counts our perfect matchings just as well as the permanent we had earlier. As a little sanity check, let's actually use our new method for counting domino tilings and see if it coincides with the result from the 2×n case. For convenience, we will equivalently consider an n×2 board and label the vertices of the ith row of the board with I. The weighted by adjacency matrix then looks like this. And fortunately, the values do not only align for 1 and 2, but for general n, by expanding the last row, we get back Fibonacci's formula again. It is also good to note that our scheme not only works for rectangular grid graphs, but for any subgraph that forms a region without holes. Now, just having to calculate the determinant is already pretty nice, but we can do even better condensing this result into one single formula. To find this closed form solution, of course the first thing we'll try is to calculate the determinant of b directly. But, and you can trust me on that, this will not be successful. So we will have to come up with a workaround. Let's actually look at the normal adjacency matrix, which, if we were to first enumerate the black and then the white vertices, just has the following block matrix form, where B is our original weighted by adjacency matrix from before. Now, since swapping rows only changes the sign of the determinant, we can bring this into the following shape, where B transpose and B are on the diagonals. And the determinant of this is obviously the determinant of B squared. So all in all, we get that the value of K's determinant is the one of B squared. You might say that looking at K instead of B seems redundant, but working with K actually turns out to be much nicer. If we were to enumerate the vertices in a more natural way, so for example just row by row, there are some natural patterns emerging with clear diagonal lines. If we are able to compute all of the eigenvalues, the product of the eigenvalues would equal the determinant. As a reminder, since we are working with complex valued matrices, the characteristic polynomial always decomposes into linear factors with lambda I just being the eigenvalues of our matrix. Plugging 0 for x, we get the determinant of our matrix on the one side and the product of all eigenvalues to the power of their multiplicity on the other side. Before we dive into the determinant problem, let's think about the structure of GMN. Similar to how we can think of a plane being the product of the x and y axis, we can think of the grid graph as the product of two paths. Concretely, GMN is the so-called Cartesian product of the paths of length m and n. Here, the vertices are the ordinary Cartesian product of the path's vertices. So with vertices of the one path in the first component and vertices of the other path in the second component. Two vertices are connected by an edge if they are the same in one argument and the vertices in the other argument are connected, which is exactly what gives us this grid structure, since edges can connect two adjacent vertices either horizontally or vertically. In a second, we will see that because of this construction, we can derive the eigenvalues of the grid graph from the eigenvalues of its Cartesian components. So let's first calculate the eigenvectors and eigenvalues of the paths, and to do that, it is actually helpful to first calculate the eigenvalues of the cycle. What makes the adjacency matrix of a cycle really nice is that it is the sum of two shift matrices. These may be interpreted as the two directed cycles our undirected cycle is made out of. The first matrix moves the components of a vector downwards, with the last component moving up to the first. This means that if you apply the matrix n times, you just end up with the same vector. On the other hand, if we were an eigenvector of that matrix to the eigenvalue lambda, multiplying by the matrix n times is equivalent to multiplying it with lambda to the n, so lambda to the n needs to be 1. So, lambda is one of the nth roots of unity, and up to multiples, every corresponding eigenvector just a list of the first n powers of lambda. The second matrix moves the components upwards, which just means that it is actually inverse to our first matrix. So this matrix has the exact same eigenvectors as the first one, but to the eigenvalue of lambda to the minus 1 instead of lambda. To literally sum it up, the eigenvalues of Cn are of the form lambda plus lambda to the minus 1, where lambda is an nth root of unity. Or more explicitly, as twice the real part of lambda, 2 cosine 2 pi k divided by n, where the corresponding eigenvector is the list of powers of e to the 2 pi k I divided by n. Notice how, by symmetry, the eigenvector generated by lambda and lambda to the minus 1 are both to the same eigenvalue. Let's move on to the adjacency matrix of a path. For a path of length n, we will consider the cycle of length 2n plus 2 and then cut off some bits later. The eigenvector generated by our lambda and its inverse both correspond to the same eigenvalue 2 cosine pi k divided by n plus 1, so that difference is also an eigenvector to that eigenvalue. Their difference is non-zero, but has 0 entries in the first component and the n plus second component, since there we just get 1 minus 1 and minus 1 minus minus 1 respectively. Now look at what this means structurally. The adjacency matrix of our path is contained in the adjacency matrix of our cycle as a block matrix, and as the first and n plus second component are 0, we can just change the adjacency matrix in those columns while still keeping our eigenvector. So we just cut the cycle in two, basically restricting ourselves to the second to n plus first component of the vector in the corresponding block matrix. This shows that the eigenvalues of a path are 2 cosine pi k divided by n plus 1. Now for the grand finale, let's finally make use of the fact that our grid graph GMN is the product of PM and Pn and index our matrix explicitly with the vertices. It will turn out that the eigenvectors of GMN's weighted adjacency matrix K are basically the product of the eigenvectors of PM and Pn. For eigenvectors v of Pm and w of Pn to eigenvalues lambda and mu, we define a new vector that is in a certain sense the product of the two. We index the entries with m times n and set the xyth component to be the product of the xth component of v and the yth component of w. Then, looking at the xy row of k multiplied with our vector v tensor w, we get the following expression, where we have equality because the term in the sum can only be non-zero if the vertices are adjacent. Now, accounting for the weights we apply to vertical and horizontal edges respectively, this simplifies to the following two sums. Each of the sums only depends on one of the variables, so we can pull the other one out and get that v tensor w is in fact an eigenvector with eigenvalue lambda plus I times mu. So, knowing the eigenvalues of Pm and Pn, we get that the eigenvalues of k are the sum of these two cosine terms, where x and y range from 1 to m and 1 to n respectively, and we finally arrive at the astounding fact that the determinant can be expressed as the following double product. And as we have seen before, the number of domino tilings of an n by n board is just the square root of this. This is the formula for the number of tilings that we have wanted all along. But it is also worth mentioning that it is truly amazing how this expression, containing roots, irrational and imaginary numbers, actually always evaluates to an integer. At least for some values, you can see the correspondence to our original problem. If m and n are both odd, then n plus 1 and n plus 1 are both even, and the n plus 1 half, n plus 1 half term in the product vanishes. Also, maybe to amaze kids that just learned about trigonometry but don't know anything about complex numbers, you can get rid of the I as follows. If both m and n are even, then we have the following simplifications of the cosine terms, so the product simplifies like this. And we can actually count the number of perfect matchings for even m and n using this real formula. It turns out that in general we have to round up the upper bounds, which will make the formula work in cases where at least one of m and n is odd. But we have done enough tedious calculations for now, so we will leave it at that. Even though it took us the entire video to develop this theorem first derived by Fisher, Kasteleyn and Temperley, we really are just scratching the surface. The first generalization would probably be to allow holes in our board. In this case, our formula still works sometimes, but sometimes it also fails. You might also naturally ask the same question, but for different dominoes or different shapes making up the board. What is the number if we consider higher dimensions, or maybe work on a torus instead? On the graph theory side, while computing the number of perfect matchings in a graph is a very hard problem, the class of graphs for which our signing trick works are called Pfaffian, which does have to do with the Pfaffian you may know from linear algebra. In particular, it is actually known that all planar graphs are Pfaffian, and a signing can be found using the so-called FKT algorithm, named after the physicists who also came up with our main theorem. Maybe going back to tilings, there's a very curious phenomenon happening if we look at random tilings from certain large mutilated boards. If we color the dominoes depending on how they are placed on the board, we see a distinctive circle in the middle of the board. In general, even for other tilings, a similar thing can be observed. Finally, although the last formula we derived is not really of any direct practical value, you would get a lot of rounding errors with those cosines very quickly, it is just as important and as beautiful as the previous practical steps. Mathematics is about finding new and surprising connections, regardless of how practically useful they turn out to be.